So I'm going to back up a little bit to something that I dropped off of test 2. Only because I forgot to open up the questions on that, but this is polarity. And this ties directly into our next subject in chapter 6. So I'll go back over polarity. First of all, this periodic table that I give you guys, I'll give you this again on the next test. But realize I use this periodic table because it has the name, it has the symbol, it has the grams per mole, and that's typical of all periodic tables. But this also has this number in the bottom right here. That's the electronegativity. So if I ask you, what is the electronegativity of carbon, you can say 2.5 electronegativity. But what's really key is not just the electronegativity. So I do EN for electronegativity, just so I don't have to keep writing that big word. It's the electronegativity difference between two atoms in a bond. Let's say we were looking at this molecule. So in this molecule, there's C to C bonds, carbon to carbon. There's carbon to hydrogen bonds. So this bond, this bond, this bond, this bond, this bond. And there's one carbon to fluorine. All those bonds exist in this molecule. You with me? Polarity is, so a molecule, I won't say that. Okay, so electronegativity. So carbon electronegativity is 2.5. I need to look at the electronegativity difference between these two. So I would do this, 2.5, that is a difference. This minus this, absolute value is 0. So you would look on the periodic table, you get the electronegativity of the two things you're talking about. You find the difference and you just take the absolute value. So this one's 0, that tells you there's 0 polarity in this bond. Electronegativity refers to the ability, the strength of an atom to pull electrons towards itself. Since carbon is the same, this is the same atom, carbon to carbon, they pull on the electrons the same degree, so they end up with 0 electronegativity difference. So there's no polarity there. Carbon to hydrogen, that's 2.5 for carbon. And for hydrogen, it's 2.1. So the difference there is 0.4. And carbon to fluorine, so if you look up fluorine on here, 4.0. So that's 1.5. All right. Here's the standard you go by. The electronegativity difference is less than 0.5. Next one is between 0.5 and 1.9. And I don't mind giving you this on the test. So this is in your book. These cutoff points are a little bit arbitrary, but we'll go by what this book says. So this electronegativity difference is that here, here, or here. Does that mean it's polar, non-polar, or ionic? This one's non-polar. So these bonds are non-polar. That means the carbons are sharing the electrons to the exact same degree. So one side of it isn't slightly negative and one side of it isn't slightly positive. It's perfectly neutral. Point 4, there's a very small difference here. Carbon is the more electronegative, so carbon is pulling the electrons towards itself. But because this is so small, the 0.4 isn't even quite 0.5, much less higher. So this is what I mean by arbitrary. There is a little bit of polarity there, but it's not enough to affect the properties of the molecule, so we just consider it nonpolar. If it's not at least 0.5, or I should say, if it's not greater than 0.5, the electronegativity difference, we just assume that it's nonpolar. It's sort of a cutoff point for actually being able to affect the properties. And we'll talk about those properties either today or next time. This one, electronegativity 1.5, that's in this range. It's between 0.5 and 1.9. That's a polar bond. And what that means is, we use this little symbol. This is a lowercase delta Greek letter, but we go, I'm talking about this bond right here. It's slightly negative here, actually pretty strongly negative because this is 1.5. It's slightly positive here on the carbon. So this negative, slight negative is on the fluorine, and the slight positive is on the carbon. Meaning fluorine has a really strong ability to pull the electrons towards itself. The electrons in this bond, there's a pair of electrons here. Fluorine's kind of winning the tug of war. It's pulling those electrons towards itself. So this is a polar bond. And what that means to the properties is this molecule versus a molecule exactly like this, but with hydrogen here, the difference between those two is these molecules will stick to themselves. Like usually you have like a beaker or something, a bulk sample, something like this. And those stick to each other more than they would if this was a hydrogen. So we'll get to the properties later. But just figuring out what polarity is, what is the polarity of this molecule, you get polarity from this. And ultimately we'll talk about what that does to its properties, but it just makes them stick to each other. So I will give you this on the test, just like I always do. You don't have to memorize these numbers. Do notice though, we talk about this as a general trend on the periodic table, kind of like size. Like I said earlier, size increases as you go down, size decreases just a little bit as you go from left to right. Here's another periodic trend. Polarity, actually electronegativity, increases generally as you go from left to right, and it increases as you go from bottom to top. If you ignore these are essentially, there's no polarity really with these. But if you start here with the halides, going right and up, this is the most electronegative atom on the periodic table. Fluorine is the most electronegative on the periodic table. 4.0, 3.5, 3.0. But you don't have to memorize them, just realize this is how you use them to figure out whether something's polar or not. And just to show you some problems, so I've backed up to chapter 4 here. So using the electronegativity values, that's those on the periodic table, classify the bond form between these two elements. So hydrogen and bromine. All right, the question is this nonpolar, polar, or ionic? You would look at your periodic table and go, hydrogen is 2.1. And what is it for bromine? 8. And what's the difference? So where does that fall on this scale? Is it nonpolar, polar, or ionic? That's how you would solve that problem. How would you classify? Using electronegativity values, classify the bond form between the pair of elements. Polar, covalent, or ionic. Just to be complete, most books say polar. It's a polar covalent. It is a covalent bond. It's polar, so they say polar covalent. Nitrogen and carbon, the next one here. So what's the electronegativity of nitrogen? It is 3.0. And carbon is 2.5. Here we have a difference of 0.5. So this one's just barely polar. You can compare polarities. This one's 0.5, so if it's less than 0.5, it's non-polar. If it's 0.5 to 1.9, it's polar covalent. That one's just barely polar. You see what I'm saying? And if we compared N to C bonds to H to Br bonds, we could actually say this one is more polar than this one. That positive and negative charge is created by the polarity. That positive charge and negative charge are slightly stronger in H to Br than they are in nitrogen to carbon. Does that make sense? So I put in, I think I already opened it too. Polarity, here it is. So you can go through these problems and see if you can solve them, but they're all done like this. They all use this as the standard to go by whether something's polar or non-polar. So I think y'all can answer these. Questions like this, which element is more electronegative than sulfur? You just look at the periodic table. Use your periodic table if you don't have one printed out. It's literally this one. You can print it off the D2L, but this is the one that I gave you on the test. It has the electronegativity values. Okay, polarity. So that's straightforward, right? It's just a simple subtraction. You go by this rule. I don't mind giving you this on the test. The only twist in polarity is this odd thing about symmetry. H to Br, let's do H to Br. Now let's keep H to Br. Actually, I'll do chlorine. The only weird twist about polarity is draw something here. So here's a molecule. Just remember this right off the top of your head. It'll be especially useful next semester when you talk about carbon molecules. But carbon-to-carbon bonds, that of course has an electronegativity of 0, so there's no polarity. And just remember this, carbon and hydrogen, those are also nonpolar. They fall below 0.5. So hydrocarbons, chain of carbons with hydrogens on it, are always nonpolar, unless there's something else there. But I've got this fluorine here. And if we calculated the electronegativity difference of carbon to carbon and carbon to hydrogen, like I said, those would be less than 0.5. Carbon to fluorine, though, 2.5, 4.0, numbers from the periodic table. So of course we get here 1.5 for an electronegativity difference. So this is surely polar. And because the fluorine has a stronger electronegativity, the negative side is on the fluorine, and the positive side is on the carbon. That definitely has a polar bond. So here's the weird thing. If I point here, I would say this, there's a polar bond right there. And that polar bond makes this overall molecule a polar molecule. So there's two different concepts here. You ask yourself that question, the answer is yes for this molecule. So because there's a polar bond there, that makes this molecule polar. Saying that the molecule is polar is we're really referring to the fact that these molecules will be attracted to each other rather strongly. This negative will be attracted to the positive in another one of these molecules. And the positive of this molecule will be attracted to another negative of this molecule. But here's the twist. If I have this, all 4 of these bonds are polar. We also call this a dipole, just in case I start using that word and I haven't told you what it is. We will draw this little arrow like this. So the way I've drawn that literally refers to something known as a dipole, and that's what this is, a dipole. It's got a pole over here and a pole over here, it's a dipole. So that's really just vocabulary. But when we use this arrow, the arrow is the negative side in this fancy way I've done the tail of the arrow. It kind of looks like a plus symbol, that's the positive side. Just a notation. So there are 4 dipoles here, but the thing about it is they cancel each other out. Meaning if I asked that same question, here are the 2 questions about that molecule. This molecule, I would say, are there polar bonds? Yes, there are 4 polar bonds there. You with me? There's 4 polar bonds there. But if I said, so is it a polar molecule? It's not, because it's so symmetrical that all those dipoles cancel each other out. That's the twist with polarity. So polarity is very simple in what I started to explain here. Are there polar bonds? How polar are they? You can answer those questions very easily. But then when you have to decide whether the molecule is polar, you have to think about it 3-dimensionally and decide if those dipoles are canceling each other out. You remember tetrahedral? So this, I can't really draw this on the plane of the board because this molecule really isn't in the plane. It's tetrahedral. You know, it's just like that. In the real world, there's 4 things around a central point, right? That's what tetrahedral is. I'm not quite doing it right, but the tetrahedral shape doesn't fit in the plane of the board. It's actually a 3-dimensional structure. And those all point directly away from each other. These arrows are all pointing directly away from each other from a central point, and that symmetry makes them cancel themselves out. So it's not a polar molecule, even though it has those polar bonds. That's the twist with polarity. That's where people get confused on polarity. You have to start to think. You have to start to think, you have to go back to molecular shape and think about, are these pointing away from each other? Is it perfectly symmetrical? And it cancels out. So that's the twist with polarity. That's the only thing that makes it complicated. Other than that, thinking 3-dimensionally, it's just a simple. Polarity is very simple until you have to think 3-dimensionally. Like, here's another example. So this would be trigonal planar. These are not polar bonds, but if you pull out the periodic table and you do your electronegativity difference, you'll find some polarity here. There is a dipole here, but it's only that one dipole. There's nothing there to cancel out that dipole. So this molecule will be polar. If you ask the individual questions, is that polar, is that polar, they won't be. But this one, you'll find out this bond is polar. And then you have to step back and go, okay, is this a polar molecule? And this is a polar molecule because there's nothing to cancel out this dipole. So that's polarity. If you trail back, that's something I did go over in the past. I just dropped it off of test 2. But I just let it go because we were going to run back into the need for polarity. And you got here intermolecular forces. All right. Are there any of these? So label the polar bonds and then decide if the molecule is polar or non-polar. Carbon to chlorine. So let me draw that molecule. So you have to look at the overall molecule and think about the symmetry. 4.71, label the polar bonds and decide if each molecule is polar. All right, so I will draw the molecule. All right, is carbon to chlorine polar? That's the first question to ask. And carbon is 2.5. Chlorine is 3.0. So these bonds are just barely polar. If I drew the arrow, the dipole, I would do this. And if I drew this in, it would be slightly negative, slightly positive, because chlorine is 3.0 and carbon is 2.5. That means the chlorine is the negative. But here's the thing, this is a perfectly symmetrical molecule. There's that dipole, there's that dipole, there's that one, and that one. Do you see the symmetry? And this does fit in the plane of the board. This is trigonal planar, this is trigonal planar here. So those cancel each other out. So that's the only twist. It's like it's very simple. Polarity is a very simple idea when you're just looking at bonds. Then when you back out to decide whether the overall molecule is polar, then you have to think 3-dimensionally like this. And suddenly it takes some critical thinking instead of just a simple calculation. Okay. So molecules, if you can decide whether a molecule is polar, and to the degree to which it is polar, you can figure out some basic things about the properties of that molecule, which is where we go next. So that was a little bit back from chapter 4. Now I'm going back to chapter 7.7, intramolecular forces. There are 3 main intramolecular forces. I'll do water here. If I pulled up the periodic table and I said, okay, is this a polar bond? You would find that this is a polar bond. Hydrogen to oxygen is a polar bond. If you have a bunch of water together, say in a beaker or in a glass of water, you have this attraction. Let me sketch in the dipoles. And again, thinking three-dimensionally, this is the bent shape. And these dipoles don't cancel each other. If you had 4 things around this oxygen that all pointed like this, then they would all cancel each other out. But this is essentially tetrahedral, but we call it bent. And these dipoles can't cancel each other, so this molecule is polar. You won't have to calculate these, but just realize this arrow and this arrow kind of add together to make one big arrow that's like that. So this is the negative side and it's positive over here. Think of this as a big positive area over here and this is a big negative area. Water is polar. It is a polar molecule. It has 2 polar bonds that don't cancel. And it's that polarity that creates this strong attraction between essentially the electron pairs here, which are negative, those are electrons, and that hydrogen. And this hydrogen will be attracted to this negative area here. So there's a big negative area here and big positive areas here. Water molecules are attracted to each other based on that polarity. That's an intermolecular force. When I say intermolecular force, intermolecular forces, it sounds very sophisticated, but we're always talking about an attraction. The force is the force of attraction when we say intermolecular force. And they're either strongly attracted to each other or weakly attracted to each other, and you can figure out properties of them based on that. So there are 3 specific intermolecular forces. 2 of them are related to polarity. There are 3 of these. Okay, the strongest one by a long shot, I'm going to say attraction, just to remind you that these forces are attractive forces, is hydrogen bonding is the strongest by far. It's kind of a misnomer. Like if I had this, if I drew this molecule for you, and I said, what's going on here? You might be tempted to say that's hydrogen bonding. That's hydrogen bonding to carbon. This is kind of a misnomer though. All this time I keep talking about covalent bonds. This is a bond. Atoms bond to each other. I say the word bond. Now we're using the word bonding here. We're not talking about this line between two atoms. It's just, it's unfortunate that chemists decided to call this hydrogen bonding. The hydrogen bonding is really between two molecules. Let me bring the water back. Here's another water molecule. It's this dotted line I'm talking about. That's hydrogen bonding. So I apologize, chemists decided to make this confusing, but that's the hydrogen bonding intermolecular force I'm showing there. It's not this hydrogen covalently bonded to this oxygen. It's not this hydrogen sharing its electrons with this oxygen. It's a completely different thing. It's just this positive area of this molecule being attracted to the negative area of this molecule. And really specifically, I might as well say this because it's true with all hydrogen bonding. It's really the hydrogen being attracted to these electron pairs. That's hydrogen bonding as an intermolecular force. So don't get confused. The strongest attraction between molecules, called hydrogen bonding, is not a covalent bond. It's literally an attraction between two different molecules. And then a good bit down the scale is dipole-dipole interaction. I'll just say mid, since I'm doing a scale here. So the mid, but by a pretty good gap. Dipole to dipole interaction, and then the weakest. London dispersion forces. I almost always just say LD forces. This one's kind of hard to explain. It's really a quantum effect and a few other weird things. But even a molecule that has no polarity, or let me do this. These two, those two forces are based on polarity, that positive and negative side of a pole, of a dipole. This one's just a little weird, and we won't go into the details, but just realize all molecules have London dispersion forces, whether they have polarity or not. A completely non-polar molecule, if I make it just carbon and hydrogen, that still has, and again, it's attraction. These still have a slight attraction to each other. If I have a bunch of these in this would be a gas, so it would have to be in a sealed container or whatever. It's true of liquids if it was liquid as well. If I have a bunch of these in a container, there's still a very small amount of attraction among these, despite there being no polarity, no positives and negatives. So that one's weird, I won't go into it, but it's just a very weak attraction. So all molecules have some attraction to each other. So if there's no polarity at all, they still have a very slight attraction to each other. If there's some polar bonds in there, but the polar bonds don't cancel each other out, there will be a dipole-dipole interaction. Let me So if you had a bunch of those together in a beaker, there's a slight attraction with that negative to that positive, and that negative to that positive. This is a polar bond, C to Cl, slightly polar. So once you get a little polarity, now you have London dispersion forces among these, because all molecules have that. But this one, these are a little more attracted to each other. Let me redraw my hydrocarbon. These two molecules I'm drawing right here, these have a slight attraction to each other. They have LD forces, slight attraction. These have LD forces plus dipole-dipole. Dipole-dipole. So these are a little more strongly attracted to each other than these are. And I'll get to the hydrogen bonding in a minute. That one's actually the most straightforward. But let me allude to the property here. These are only slightly attracted to each other. These have that slight attraction, but they also have a stronger attraction because of the dipoles that are there. If you took a sample of this, and let's say it was liquid, these would actually be gases. But let's pretend this is a liquid and this is a liquid. And I have, in beaker A, I have these. And in beaker B, I have the other ones. And I set them on a hot plate and I start turning up the temperature. These are gonna boil at a lower temperature than these will. Let me explain this. If you have a solid, so these are two atoms in the solid, fused, stuck in a solid form. When you start increasing the temperature, they start vibrating. So watch this. Let me take it from a solid to a liquid to a gas. They start vibrating. And you put a little more heat in, they start vibrating more. Putting heat in, I mean temperature. You're raising the temperature. Put a little more heat in, now they're really kicking around. And then you get to a certain point where they actually come away from each other. They're able to like swim around each other. They're still attracted to each other, but they're vibrating and now they're moving. So the heat you're putting in is making them move around. Now you have a liquid. They're still stuck to each other, but they're moving around. You put in more heat, they start moving faster. You put in more heat, they start moving faster. Then you get to a point where one of them finally shoots away. When they start shooting away like that, now it's boiling, now it's becoming a gas. That's what's going on with the molecules in the sample. So you start heating these, they're trying to overcome their attraction to themselves. You see what I mean? Taking it from a solid to a liquid is overcoming the attraction. Taking it from liquid to a gas, it's overcoming that attraction. So these that have stronger attractions to them, you have to get it to a higher temperature just to get it to melt. And you have to get it to an even higher temperature to get it to boil compared to this one. That's one of those properties you can predict. If you can look at the structure of this molecule and just the structure of this molecule, you can look at it and go, oh, this one's gonna have a much higher melting point and a much higher boiling point than this one. See what I'm saying? Properties that you can predict based on intermolecular forces. All right, hydrogen bonding is just kind of a special category of, it's essentially very, 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 very polar bonds. And those just end up in a special category. They're so much stronger, these attractions, that they just go in a separate category. And it's very simple. What you have to remember, there's only 3 bonds that you can make from the entire periodic table that have hydrogen bonding. It's H to O, it's H to N bonds, H to F bonds. If you see those in a molecule, then that molecule has these very, very strong attractions to each other. And you would predict accordingly. It's going to have a much higher boiling point than otherwise, much higher melting point than otherwise. Think water. Each water molecule can make 2 hydrogen bonds. And actually, in all these cases, so here's water. In all these cases, it's the hydrogen being attracted to a pair of electrons. Ammonia, it's not just water or just ammonia. It's anything that has N to H bonds, anything that has O to H bonds. But I'm just using the most fundamental example I can here. Hydrogen being attracted to the pair of electrons on another molecule. And then the last one, HF. If we did the Lewis structure, we would have all these pairs of electrons. That's it. The only three examples there are for hydrogen bonds. It's just that these are so strong that it's an obvious physical effect if you're boiling and melting. Intermolecular forces. And questions about intermolecular forces always come down to, you look at the structure, you're looking for O to H bonds, N to H bonds, F to H bonds. If you see those, of course you have to decide whether it's symmetrical, because if it's a symmetrical molecule, despite the fact that there are hydrogen bonds there, despite the fact that you have this extreme polarity here, it still will behave as if it's nonpolar if it's symmetrical around the bonds. But otherwise, if you have N to H or O to H or H to F, you have very strong attractions among the molecules. All right, let's see. Yeah, all the examples in the back of the book for intermolecular forces use these colorful diagrams that I never use on a test and I never give you on the quizzes. So let me open this up and just show you what these look like. Intermolecular forces, preview. These all give you a diagram to look at like this. It's not those three-dimensional things with color. So learn like this, but we'll go through those in the back of the book, but I'll draw these on the board as I go through it. But they all look like this. You just look at the molecule, you decide what you're thinking. So like this one, which one has the lowest boiling point? This has nothing but carbon to carbon and carbon to hydrogen. The only intermolecular force here is the LD forces. This one, this has the O to H. This is going to have a really strong attractions. This is going to have probably the highest boiling point among these. If you calculated the dipole, the electronegativity difference for oxygen and carbon, you'd find out this bond and this bond are slightly polar, or maybe it's a good bit polar. So these will have attractions to each other, but they don't have the hydrogen bonding. So if I wanted to rank these four, this one's going to have the lowest boiling point because the only force it has is this very weak London dispersion force. It doesn't even have polarity anywhere. This one, you definitely have some polarity here. And like I told you, just something to just memorize. Carbon to hydrogen is always nonpolar. So there's so many hydrocarbons in the examples of molecules you'll see that it's just worth knowing. That's nonpolar. And carbon to carbon is nonpolar, but really anything to that same anything is always going to be nonpolar because when you find the electronegativity difference, it's going to be zero. So carbon to carbon is nonpolar, carbon to hydrogen is nonpolar, so this whole molecule is nonpolar. So its only intermolecular force is this very weak one. See what I'm saying? This one has some polarity here, and it's also got this extreme polarity, the O to H bond. So this has hydrogen bonding and polarity, so these will stick to each other pretty strong. This one has the polarity, the oxygen and carbon. It doesn't have hydrogen bonding, so these attractions will be weaker than these attractions. You see what I'm saying? And this one is just going to be very similar to this one. So you could actually rank these on which one has the highest boiling point. This one's going to have the lowest boiling point, so that's the answer to this question. This one's going to have the middle range boiling point, and this one's going to have a very high boiling point comparatively. Follow that? Intermolecular forces comes down to those four things. Let's go through which of these, okay, and these are giving, the B and C here on 7.60 is giving you the formula, not the actual diagram. I'll always give you the diagram. Rather than test your ability to build the structure out of these. The CO2 looks like this. Instead of saying CO2, I would give you this. And the other one there is Br2, that's just gonna be, there's of course no polarity here. Electronegativity differences are gonna be 0 here. Carbon and oxygen, no, that's some polarity, but this is linear. So it's gonna cancel out and that won't be polar either. That's the tricky part. This is linear. You have two dipoles that cancel each other out. This one, I guess you could say is linear, but it's not. Same electronegativity for bromine, so that's going to be an electronegativity difference of 0, so no polarity there. And this molecule is not polar. So what's the question? Okay, hydrogen bonding. Of course, there's no hydrogen bonding here. Hydrogen bonding only shows up if you have H to F, H to N, or H to O. So we're looking for those bonds here. So the only one of these 4 in 7.60 that has hydrogen bonding is D, because it's got N to H bonds. You see that? Let me draw these. This is saying which intermolecular forces are present. Instead of giving you those colorful three-dimensional diagrams, I would have given you it's just got an oxygen here. I would give you this. And like I keep saying, carbon to hydrogen is nonpolar, carbon to carbon is nonpolar. But there is a little polarity here between carbon and oxygen. If you looked at the periodic table and did your electronegativity difference, you would find that you're just barely in this range for those. So every molecule has this. So this is asking you, what intermolecular forces do these molecules have? Every molecule is going to qualify for that, whether it's polar or not. All molecules have this. Your next question is, does it have dipole-dipole? And since there's a dipole here, then this also has dipole-dipole. And now your last question is, does this have hydrogen bonding? It doesn't, because it doesn't have fluorine to hydrogen, oxygen to hydrogen, or nitrogen to hydrogen. So it does not have this. That's the answer to that problem. Do that one too. Green, I think, is chlorine. I'll just use chlorine. So that next one is saying carbon, carbon, 2 hydrogens, and oxygen. That doesn't make sense. Red is always oxygen, and that's impossible. That's an impossible molecule. I love cracking on I love catching out in the textbooks when they do something just like demonstrably wrong. That's an impossible molecule. Black has to be carbon, and red has to be oxygen. There's no way you can do that. Let's go to this one. I would give you this. And question is, what types of intermolecular forces are exhibited? All right, so there's no oxygen to hydrogen or fluorine to hydrogen or nitrogen to hydrogen in here, so it doesn't have that. This is polar. If you calculated it out the electronegativity difference, you would find that this falls in this range. So it has dipole-dipole. The dipole-dipole is saying that dipole, slight negative, slight positive. This dipole this other one of these has this. I didn't draw that great, but the attraction is this negative to this positive and this negative to that positive. That's the dipole-dipole interaction, attraction. So this definitely has this, but it does not have hydrogen bonding. So it has London dispersion and it has dipole to dipole, but it doesn't have any hydrogen bonding. So it has 2 out of 3. Which compound, this or this, has a higher melting point? Okay. When it comes to melting points, and I can say melting points or boiling points. This is true of both. And when I say melting point, we always say that melting point, but what we should say is melting temperature. That's what I mean when I say melting point. It's always a temperature. When it comes to these things, size does matter. So if I compared this one is decane, that should be 11 carbons. So if I drew this in a way that's not a fancy picture, it would be when I teach 1152, I swear 1/3 of class time is me drawing in these hydrogens. Because we draw a lot of molecules like that at 1152. So we have that compared to 1, 2, 3, 4, 5 carbons. Now, if I ask you, what intermolecular forces do these molecules have? It wouldn't take you long to realize it doesn't have hydrogen bonding, and since there's no polarity there, there's none of this. It's only the London dispersion forces that these have. So picture a big sample of this in its own beaker by itself. This would be a liquid. I'm pretty sure that's a liquid too at room temperature. So I have beaker A of this and beaker B of this, and now I'm comparing their boiling points. These won't have the same boiling point. They will have a very low boiling point because they don't have these strong attractions going on. So they won't be much more than room temperature. But this one will have a higher boiling point than this one because this one has more London dispersion forces, literally because there's more matter in there. Follow that. These will have more stronger attractions to other ones of these, simply because they're bigger. That creates more attraction. So this one will have the higher boiling point. This one will have a lower point. Both of these will have fairly low boiling points. but this one will have a lower boiling point than this one. If you have two beakers side by side and you start slowly ramping the temperature up, this one's gonna start boiling at a lower temperature. And when this one boils away and you keep turning the temperature up, then eventually this one will boil. So, I'll just say the attractions are stronger if it's a larger molecule. So you can compare two molecules, and if you're comparing two molecules and both of them only have London dispersion forces, you can still differentiate which one's gonna have the higher or lower boiling point based on which one is larger. If you compare two molecules and one of them has only London dispersion forces, and the other one has, of course, London dispersion forces and dipole-dipole interactions, that one's gonna have the stronger attractions. So it's gonna have the higher boiling point. You follow this logic? And of course, molecules that have hydrogen bonding will be the highest boiling point. So this one's asking which one has the higher melting point or boiling point. It's the same idea. The higher melting point is going to be the larger molecule. This next one. So I'm going to draw these molecules the way I would on a test. Four carbons. Let's go to double bond there. No, I want to do these two. I was looking at the wrong one. So those quiz questions that I give you, they're all going to be like this. For some reason, this whole section has only these pictures. But I would have them like this on a test, and carbon, oxygen. These do have the same formula. This is an incidental fact, but it's C2H6O. These are what we call isomers, which we'll go over that more next semester. So comparing these two, which one do you think has the higher boiling point? So which one has the higher boiling point? Your thought process is this. You look at this, and of course, both of them, for sure, have London dispersion forces. All molecules have those. Carbon to oxygen is a polar bond. So they both do have this dipole to dipole. What about H bonding?
The first one has the same one.
Yes. This one has O to H bond. This one does not have any O to H bond. So which one has the higher boiling point? This one. It has those strong attractions to itself. Follow this? All right, let me give you another example. There is, here, I'll do it like this. If both molecules you're comparing only have London dispersion, so if the two molecules you're comparing only have London dispersion forces, the larger one has the stronger attraction. So the example I just gave, it was easy because one of them they both had London dispersion. They both had dipole-dipole, but only one of them had the H bonding, so you knew that one had the higher orbital. But if you're comparing two molecules that are the same on all those levels, like they both have London dispersion, and let's say they only have London dispersion, how do you tell which one has the higher orbital, whichever one is larger? If you have okay, all molecules will have London dispersion, but if the two molecules only have London dispersion and dipole-dipole, and think of this in terms of one molecule has carbon to fluorine and another one has carbon to chlorine. But other than that, they're both the same size, they're both the same everything else. It's just one molecule has a carbon to fluorine bond and another one has carbon to chlorine. You'll find if you do the electronegativity difference, this one's going to have a larger electronegativity difference, that is polarity, than this one. So then you compare which dipole is stronger. This one, the electronegativity difference will be larger than this one's electronegativity. I could calculate it out, but I would just bring up a periodic table, do my electronegativity difference. You will just literally have a higher value for this dipole than you will for this one. So if they have only LD and dipole-dipole, the one that has the stronger dipole will have the stronger attractions to itself, higher volume, higher volume. Does that make sense? And lastly, all things being equal, the word only here is kind of senseless, but H bonding. The hydrogen bonding can be random in terms of strength, just like these can. And it turns out H to F is the strongest of the hydrogen bonding. H to oxygen is mid, and H to... I kind of hate to say the word weakest with an H to N bond because they're extremely strong dipoles. But these are those three that are so strong, such strong dipoles, they belong in their own category, hydrogen. So if you have molecules that have this and molecules that have this one's going to be stronger than this one. Although usually you're comparing these two. Hydrogen to fluorine, there's only one way for you to have hydrogen bonded to fluorine. This is incidental, but I'll throw this in just so you see it. That's the whole molecule. If you have H to F bonds, you literally have these molecules. There's no other way to put hydrogen and fluorine together other than that. So that one little thing with just fluorine and just hydrogen, that's the whole molecule. That's the only way you'll ever see H to F bonds. And that's a gas at room temperature. So it just doesn't come up that much in questions. You're usually comparing these two because you can do that in many different ways. You can do that. I'm going to end class here, but the only time you will ever see hydrogen bonded to fluorine is that's the whole molecule. There's nothing else you can do, is that one little thing. But you can get many and varied different situations, oxygen and hydrogen and nitrogen and hydrogen. They can show up in large molecules, small molecules, but if you got H to F, it's only ever going to be this. So it doesn't come up as much. Okay, I think that's enough that you can do these two new. So I've got intermolecular forces and polarity is up for you to start practicing. You guys good? Are you practicing? You're gonna knock test 3 out of the park? Right.
Pass and.